In this video, we're going to use a simulation-based approach to decide whether two groups are significantly different from each other. And we're going back to that example from earlier. Do people believe that a drug is more effective if its description is accompanied by a graph? So here, where we're testing statistical significance, we're trying to use a statistic to draw a conclusion about a parameter. So remember, when we say statistic, all that is just a numerical summary of the sample. So if it's a value that you calculated from the sample, we call that a statistic. A parameter, on the other hand, is a summary of the population. So in general, we don't have the whole population, and so we're using a statistic to say something about the population. That's what inference means, just that we're taking the sample and using it to make predictions or statements about the population. And in this case, it can be like a population, a finite population, or in an experiment, sometimes it's helpful to think of it as like a long-run value. So maybe not what happens in a specific experiment, the sample that you have, but what would happen if you kept going, if you had sort of an infinitely large sample. That's another way to think about the parameter. So we want to know, when we see this difference in means between the text only and the text and graph group, is this statistically significant, or is it possible that they just came out a little bit uneven just by random chance, just because of the way the random assignment happened? So I'm going to use what's called a 3S strategy. Our book doesn't use this terminology, but if you look at section 10.3 of our book, it does a similar process. So the first step is compute a statistic. So we want to summarize the sample data. And a statistic needs to be one single number that will sort of summarize what's going on in the sample. So we've got our sample means, but that won't do it because we have one for each group. So we need some way to put them together. And probably the easiest way is just to look at the difference. So I'm going to look at the sample mean for the group that saw both the text and the graph. I'll call that TG. And I'm using X bar to symbolize the sample mean. And then I'm going to subtract the sample mean for the text only group. I'll put TO. So I'm going to do 6.833 minus 6.129, and I get 0.704. So there is a difference between the means and the sample, but we really have two explanations for this observed statistic. One of them is called the null hypothesis, and the null hypothesis is the one that we want to rule out. So in this context, the null hypothesis would be that the graph doesn't really matter. The graph makes no difference, and we ended up with a small difference in the sample just by random chance. That's the null hypothesis. And when we write this using symbols, we're going to use mu to represent the parameter. So the null hypothesis is that in the long run, the difference between the text and the graph group and the text only group is actually zero, right? That they have the same long run mean. It just came out a little bit uneven here because of the random assignment in the finite sample. The alternative hypothesis is going to sort of depend on how the question is phrased, so I've repeated it here. Do people believe that a drug is more effective if accompanied by a graph? So if I'm writing this in words, I might say that the graph leads to higher ratings. And this sounds kind of causal, but that's actually okay here because we do have random assignment. This is an experiment. So if we end up with a significant difference, it's reasonable to think that it is a cause and effect relationship. So the alternative hypothesis is that the long run mean for the text and graph is bigger than the text only, or you can say that the difference is positive. So you can think of the alternative hypothesis as the thing that you want to show. Right? We want to show that graphs really do lead to higher ratings of effectiveness, but before we can comfortably make that claim, we need to rule out the null hypothesis, right? We need to show that that's not a reasonable explanation for our data. So we're going to simulate the values that you can get from the null hypothesis and see if our sample data is in that range. So the second S in the 3S strategy is to simulate values of the statistic that could have happened by chance alone if the null hypothesis were actually true, meaning if graphs really made no difference. So the way we're going to do this simulation is we're going to write all of our ratings, the 61 from both groups, we're going to write those on cards. We're going to put them all together and shuffle them. So notice I haven't labeled them here whether they're in the graph group or the text only group. And the reason that that's not necessary is that I'm making a specific assumption here. I'm assuming the null hypothesis. I'm assuming that graphs don't matter. So in this case, you're basically saying, the ratings are what they are. Some people are going to think the drug is more effective, some people are going to think it's less effective, and it has nothing to do with the graphs, so there's no reason to label the groups. You're assuming that the null hypothesis was actually true. Then I'm going to deal them into two piles, 30 and 31, just to match my original sample size. So at this step, I'm mimicking the random assignment process. So when we say just by chance in this example, we're saying just because of random assignment. Maybe they came out a little bit uneven just through random assignment. Okay, then I need to summarize the simulated sample. So I'm going to calculate the difference in the means for the two groups. And remember, it's important to have one single number that summarizes the simulated sample. Earlier, we decided to use a difference in means, and so we want to stick with the same thing here, because basically we've got that 0.704. We don't know if that's big enough to be convincing until we have something to compare it to. So that's what the simulation is going to give us. So we've done this once, we've got our cards dealt out, we calculated the difference of means, and then we repeat that process many times. There are lots of different applets that'll do this. My favorite is probably the Rossman Chance applets, so I'm going to search for those. And I'm using the applet for two means. So the first thing I need to do is to copy paste in my data. So this is data from the textbook, and it was in a CSV file, so I can just copy it straight out of there and paste it. Notice it says graph yes or no. That's a little bit different than the way I had it before. And I'm going to click use data, and I can tell that everything went in correctly because I've got my means and standard deviations there. It's also calculated the difference in the means for me. So now I'm going over here to the shuffle options. I like to do it in plot so I can see what's happening. So it's taking all of those values when I click shuffle, shuffling them all up and reassigning them to the groups. So it's basically imagining that the random assignment had happened a different way and that they had ended up in these different groups. So you can see they've got the means for those two groups. The difference between them is 0.31, and 0.31 is what's getting graphed over on this third graph on the right-hand side. But that doesn't tell us anything really. That's just one way that the simulation could have turned out. If I do it again and reshuffle, I get different means, actually pretty much exactly the same. That's kind of a coincidence. Do it again. This time it was a negative number, so that just means that the no group was actually higher this time. So I got negative 0.41 and plotted it over here, and I want a whole bunch of those. So usually this doesn't take too long. Let's see how my computer does. I'm going to get up to 10,000 shuffles. So let's remember what we're looking at in this graph. Every dot in this graph is a difference of means. So it's the mean for the text and graph minus the mean for the text only. And this is showing the values of that statistic that would occur under a very specific assumption, right? The values that would occur if the null hypothesis were actually true. So that's why this graph is centered at 0. That's not proving anything about the real world. It's centered at 0 because of our assumption, right? Our assumption is that there's no difference between these two groups, that graphs don't actually matter. And if that were really the case, sometimes you get a difference that was positive, sometimes you get a difference that was negative, but it would be centered at 0. So is this a good explanation for our data? To figure that out, I'm going to find my sample difference in means on this graph. So I'm going to type it in here where it says count samples. 0.704 was the difference in means. And I can count and see how often that value occurs. So it looks like, let's see, 236 out of 10,000 times. So it occurs, a little over 2% of the time. So I'm finding my difference in means. I'm seeing how likely it is to get this value or more extreme, and I'm considering the values to the right, the greater than values, to be more extreme because that's how our alternative hypothesis was defined. And when I count those, when I see how many are greater than 0.704, I got 236 out of 10,000, which is 0.0236. So what is that telling us? Again, we always have to remember that this is sort of supposing that the null hypothesis were true. So this is saying if graphs really made no difference, if the null hypothesis were actually true, that's our assumption, then it would be somewhat unlikely to get results like ours, right? It only happens 2% of the time, so it would be somewhat unlikely to get results like ours or more extreme. So unlikely, that's kind of a vague term, but we can quantify it using the p-value. So the p-value is the probability of getting our sample statistic, which in this case was the difference in means, 0.704, or more extreme, and that's going to vary depending on how your alternative is defined. So here we're talking about greater than because we have a greater than sign in the alternative. If the null hypothesis were actually true, which in this case means that the long run mean for the text and graph group and the long run mean for the text only group are equal, or that the difference between them is 0. So p-values always have these three parts. It's the probability of our sample statistic or more extreme if the null hypothesis were actually true. And when we have a small p-value, that means that our sample results would be very unusual if the null hypothesis were true. So the smaller that p-value, the more unlikely it is, the stronger your evidence gets against the null hypothesis. So when we talk about the strength of evidence, we're always talking about the evidence against the null and for the alternative, right? We're trying to show that the alternative is true, but first we have to rule out the null. So the smaller the p-value, the stronger our evidence against the null. So there are different guidelines for how small the p-value needs to be before we would consider it convincing, but a common cutoff is 0.05, that if it's smaller than 0.05, that we consider it strong evidence. So I'll use that here. So I'll say that we have strong evidence to suggest that seeing a graph, that's our treatment group, that seeing a graph leads people to believe the drug is more effective. Right, that's what they were measuring with their ratings. And of course, this isn't perfectly a deterministic relationship, so I'm going to add on average. So we wanted to know if the results could have occurred by chance, and that's certainly possible, but it would be pretty unlikely to get data like ours if the null were actually true. Only happens about 2% of the time. So in this case, we have pretty strong evidence that it wasn't just chance, that there actually is a relationship between seeing the graph and thinking that the drug is more effective.